Okay, so in the last video we got a look at the implications of using the 0.01 level rather than the 0.05 level. So now we need to explore what directional hypothesis pairs yield for us. So recall that in the directional pair, the alternative is going to state the direction of expectations, and we're going to have a one-tailed test with the rejection region in the tail that's in the expected direction. As you know, the null states the direction opposite to expectations, and the equal than condition is in the logical operator for the null. And here is our alternative hypothesis symbolized by H1, that the population mean is greater than 100. I'll go ahead and read the alternative in this example. The mean parenting skills score in the population of all parents of elementary school children in your town is greater than 100 points. And of course the null is the flip-flop of that. The null states it's less than or equal to 100. Here is our decision rule for the 0.05 level when the alternative states greater than. Here's our decision rule, and it is fail to reject the null if the obtained z is less than 1.645, and otherwise we're going to reject that null. So as you know, our obtained z calculated to 2.5, our obtained z is greater than 1.645, therefore we are going to reject the null. Now do note that with decision rules for one-tailed tests, we're not going to be dealing with absolute values. We're going to be dealing with the actual value of the obtained statistic. Let's contrast a one-tailed and a two-tailed test. And let's presume that the study result is indeed in the expected direction. Think back to chapter 14. You should not be using a one-tailed test, basically speaking, unless you have quite strong expectation that the result will be in a particular direction. So what we're saying here is, yes, let's presume that the result is indeed in the direction that you expect, and almost always it should be. Now then, the rejection region for a one-tailed test focusing on the direction of expectations is larger than that in a two-tailed test, and it's closer to the value stated in the null, so that if the result is indeed in the expected direction, it's going to be easier to reject the null with a one-tailed test than with a two-tailed test. So here is a visual comparison for our example with the one-tailed test and the two-tailed test. So here our rejection region is the 5% tail in the positive direction. So this is our rejection region for the one-tailed test. The full 5% is in the tail, in the direction of expectations. And we only need to come over 1.645 standard deviations. So were you to go to the normal distribution table at the back of the text, you'd see that going 1.645 standard deviations, that's far enough to delineate the upper 5%. Whereas in our two-tailed test down here at the bottom of the figure, the rejection regions are 2.5% in each tail. So here we needed to go 1.96 standard deviations. So you can see, focusing on the direction of expectations, which is to say the right-hand side of these distributions, got to come out farther from the value stated in the null when the test is two-tailed than when it's one-tailed. So it's easier to reject the null with the one-tailed test because the rejection region is beginning closer to the value stated in the null. Let's talk almost intuitively about how do you determine the value of p in a two-tailed test versus a one-tailed test. And so with the two-tailed test, you're considering results in both directions. With the one-tailed test, you're only considering results in the direction of expectation. Now, assuming that the result is indeed in the expected direction, that being the case, then if you calculate p from the perspective of a two-tailed test, that p will be double the p of a one-tailed test. Or looked at from the other side, p-value for the one-tailed test will be 1/2 of the p for the two-tailed test. So in our example, our two-tailed p calculated to 0.0124. On the other hand, with a one-tailed p in essence only considers cases that are in the tail in the direction of expectations. So the one-tailed p in our example calculates to 0.0062. And let's take a look at this comparison visually. So here we're getting a look at the sampling distribution, and here's our study sample mean. Now, if one was calculating p from the perspective of the two-tailed test, you would consider cases that are as extreme as the study result or more extreme in both directions. So here's our study sample result. We have 0.62% that are more extreme in the positive direction, and then on the other hand, here's another 0.62% in the negative direction that are just as extreme. So when you calculate the p for the two-tailed test, the p comes to 0.0124. I mean, it's in essence the sum of the two tails, and we're dividing by 100 because we're dealing with probabilities rather than percentages. Yet it's the p calculated from the perspective of the one-tailed test. It is simply 0.0062. It only looks at the cases that are more extreme in the positive direction. Now let me just mention that as you do examples for the large sample test of the mean in this text, I mean, when you do these examples, you're not going to be calculating the precise value of p. At least most often you won't. What you'll simply be doing is using the decision rules, and you'll simply be accepting or rejecting, and that accepting or rejecting is dependent on whether the p is greater than or less than the alpha value connected with the significance level. Now I'll further mention when you go on next year perhaps to your research course, and you'll start using the computer more and more to carry out different significance tests. Well, the computers are going to actually calculate the value of p for you. And there are different alternative ways to express the hypothesis pair. Let's look at another one. So we've just done one-tailed example, and that was using the 0.05 level and with the alternative stating greater than. Now what if we continue to have the alternative state greater than, but let's use the 0.01 level rather than the 0.05 level? So here we're going to have a different decision rule. And by the way, in this course, which is to say as Rosenthal's teaching it, you're not going to need to memorize these decision rules. I'll give you those for the problems. But the decision rule is fail to reject the null if the obtained z is less than 2.33, reject the null if the obtained z is 2.33 or greater. So our obtained z is 2.50, that is greater than 2.33. Our decision is to reject the null. Now, call back to the last video and that we did a two-tailed test at the 0.01 level. And in that case, we failed to reject the null. So when we do a one-tailed test at the 0.01 level, we reject the null. When we do a two-tailed test at the 0.01 level, we fail to reject. These different results point something out to us, and that is, presuming that the study result is indeed in the expected direction, it is easier to reject the null with a one-tailed test than with a two-tailed test. So here is a visual look at our results. So in this situation, that being a directional pair, one-tailed test, alternative states greater than, 0.01 level used, the rejection region is the upper 1% and of the sampling distribution, and that upper 1%, you could consult the normal distribution table, begins 2.33 standard deviations above the mean. Our study sample result was 2.5 standard deviations above the mean. It's in the rejection region. Therefore, we reject the null. Now, I'll help us think back to the last video. But if you use the 0.01 level and a two-tailed test, well, then you would need to get out to the 0.5% tails in both directions. Those would define the rejection regions. You'd sum the 0.5 and the 0.5, and you'd get 1%. So when you use the 0.5 tails, well, they start 2.58 standard deviations away from the mean. So when we had a two-tailed test at the 0.01 level, we had two rejection regions. We split, we take the territory here, so to speak, and we move it to the other side, and at any rate, we don't quite get to 0.5% tail, but we do get to the 1% tail. Summing up, other things being equal and the result being in the direction of expectations, it is easier to reject the null with a one-tailed test. Well, there's still more possibilities to consider. For learning purposes, let's go ahead and reverse the directions stated in the null and the alternative. Now, this is for learning purposes. I'll just say intuitively why this might feel odd to you. You're delivering an intervention to help. Presumably, or possibly at least, it helps, but it's sort of far-fetched, perhaps. That may be too strong of a word to think that your intervention's going to hurt. In other words, the alternative carries the direction of expectations, and it says that the mean in the population that you work with is less than 100. So this is sort of a counter. This is an example for learning purposes. So we've reversed the direction of expectations. Here's the decision rule where the alternative states less than and the 0.05 level is used. And it calls for failing to reject the null if the obtained z is greater than minus 0.645. Our obtained z is greater than minus 0.1645, therefore we fail to reject the null. What's going on in this example? Well, in this example, the direction of expectations is incorrect. The rejection region is in essence in the opposite direction to the direction of expected results. So if the results are in the expected direction, we're always going to fail to reject the null. This is a tricky situation, and it demonstrates why you should try to stick to two-tailed test. Let's take a look visually at our result. Here is our rejection region, given that the the alternative is stating less than. It's the 5% tail in the negative direction. So you can see that no matter how far the result moves in a positive direction, the direction opposite to that stated in the alternative, the null isn't going to get rejected. So, I mean, conceivably, perhaps the result could be way out here, so that had you run a two-tailed test, a result way out here in the positive tail, it would be highly significant. It would be significant with something like p equals 0.000007. In other words, or you by chance alone, you would almost never get a result this extreme. But sticking with the hypothesis testing model, you only reject when the result is in the direction stated in the alternative. So you would not reject here, sticking with the model. So this is a conundrum. You know that a result such as this just doesn't occur by the luck of the draw, but you're stuck because you have a directional pair with the alternative in the wrong direction. You're stuck failing to reject the null. So pragmatically what you would do is you'd say, I goofed. I used a one-tailed test where I should have used a two-tailed test. Why should you have used a two-tailed test? Well, if the result is so far in the direction opposite to expectations, your expectations, given the alternative states less than, your expectations were in the wrong direction. Clearly, you didn't have a good sense of what the results might be. And since you didn't have a good sense of it, as demonstrated by the fact that the result was in the opposite direction, you should have used a two-tailed test. So my advice is you'd repeat the study, but this time not repeat the study, you'd repeat the significance test, and you'd use a two-tailed test. And this is regarded as cheating in the sense that it's easier to reject the null with a one-tailed test, so people like to do that. But you really should not do that unless you're strongly convinced in the direction of results, because just running the test again to get the right result is not kosher. Here's our final combination of significance level and type of test. So we have, in this case, the alternative stating less than, and then we are using the 0.01 level. And here's our decision-making rule. And in this situation, we would again fail to reject the null. And I've made a mistake here. This should say minus 2.33. But it's the same basic situation as we encountered last time. The actual result is in the direction opposite to expectations, and one shouldn't be using a one-tailed test in a situation such as. Okay, we've completed our different combinations of directional and non-directional pairs, and using the 0.01 level and the 0.05 level. So let's step back a little bit and just talk about significance testing. And as I talk about results, let's presume that we have indeed rejected the null in this situation. So we've rejected the null. Basically, that's telling us that chance alone is an unlikely explanation for the result. The fact that the result is unlikely to be due to chance in essence conveys to us that something real is at work. The explanation of the null, that the difference is due just to chance, that's insufficient. Our data contradicts that notion. We need a more complex explanation. Well, the alternative hypothesis in essence states that the difference that you see is real. In other words, it's a difference at the level of the population, not just a figment of the luck of the draw of the random sample. So we've got a real difference at work. And the fact that we've got a real difference, therefore that tells us, yes, we can go ahead and really think seriously about what this real thing is that's causing our study sample result. And so I thought I'd just talk through some of the real things that might be leading to the difference that we see here between your study result of 105 and the value in the null. So we're presuming that's a real difference. Well, it may be that your intervention actually increased parenting skills. On the other hand, the real difference may indeed reflect perhaps simply that parenting skills in the city where you work were high prior to your intervention, and that's why the parents did so well. Now, maybe you have a particularly personable personality and very good communication skills, and to oversimplify, perhaps simply the parents in your study sample who worked with you with your parenting skills intervention, perhaps they liked you. And since they liked you and since they sensed your dedication, they fudged their responses on the parenting scale. In other words, they gave socially desirable responses. Their parenting perhaps really isn't better than that in the large national sample, but they fudged their responses on the measure. Or perhaps their parenting really has improved. Now, why has it improved? It has perhaps nothing to do with the scientific components of the intervention that you've delivered, but perhaps the improvement reflects the sort of the extra attention and concern and empathy that you demonstrated in your intervention with them. Or indeed, it might be some combination of these above things or something completely different that is the explanation for these study results. So, I mean, the big message is we only consider the real things that might be responsible for a difference when we eliminate chance as a plausible cause. In other words, when chance alone becomes an unlikely cause. So eliminating chance is not precisely the same thing as being able to conclude, well, there's a causal relationship due to your intervention. But we know because the difference, or at least I don't want to say we know, what I want to say is we're confident that the difference is due to some real thing. And oftentimes it's difficult to figure out what that real thing is, and sometimes one research design lets us draw conclusions, whereas another might not. Chapter 15 was a big one, and we've made it through it.